Okay, my clock says it's 15:30 now, so maybe we start. So welcome all of you to this session of the FSTTCS conference. We'll have 4 talks in this session. And the first talk will be given by Aishwarya, but before we go into the talk, we'll keep the questions to the end. That is, the speaker give a talk for less than 10 minutes, and we'll have a short question answer session in the end. So the first talk will be by Aishwarya, and she will tell us about weighted tiling systems. Aishwarya, over to you.
Thank you, Prakash. So today I will be presenting to you our results on the evaluation complexity of weighted tiling systems for graphs. This is a joint work with Paul Gaston, who is here in the audience. He's from LSV in Paris-Saclay, and I am from Chennai Mathematical Institute. So we will start seeing what this formalism of weighted tiling systems are, and then how we will possibly see a very quick example of how these weighted tiling systems can be used to model algorithmic problems on graphs. And then we will see our results on the evaluation problem and the results on the complexity and the case of bounded tree width graphs. So for words, if you have a set of words, there are finite representations for this, effective finite representations for this, like finite serial automata, logic, etc. And now from sets of words, if you want to lift it to functions from words to some weight domain, we have this weighted automata, weighted logics, etc. So this is the situation for words. Now what about graphs? So if you want to represent again sets of graphs, we have similar notions like graph acceptors or logic. And now in the same way, one can ask whether there are finite representations for functions from graphs to a weight domain. And for this also there exist representations like weighted tiling automata, weighted logics, etc. And our talk will be in this direction, but we will be concentrating on the evaluation problem. So let us look at what is this weighted tiling systems. So weighted tiling system is a finite representation, as I said, for representing some functions from graphs to a weight domain. So these graphs are node and edge labeled graphs. The labels come from a finite set. And such graphs include binary trees or grids. For example, here is a grid. And the weight domain is equipped with 2 binary operations that make it a semi-ring. So we have a wide variety of semi-ring example, like natural semi-rings or tropical semi-rings. So how does this weighted tiling system assign a weight to a weight to a graph? So this is by means of a tiling or a coloring. For this, a weighted tiling system has a finite set of colors or states. So here is an example with just 2 colors, blue and yellow. Suppose we have a graph. Here is a grid. This is one example of a coloring. This is another example of a coloring. And we don't want to allow all the colorings, and we want to assign weights to some colorings. So for this, what we have is a set of permitted tiles. A tile will have a central node and its neighbors, and then it will say what kind of colors they can have. So we will have this set of tiles for every type of node. So this node has 4 neighbors, this node has 3, and this node has 2, and so on. So for all of these kind of things, we give the set of permitted tiles, and for each such tile, we will also give a weight for each of those tiles. Okay. Now, how does it give the weight to a graph? So first of all, you consider you give a weight, first of all, to a coloring or a run. So coloring is like a run. So how do we give a weight to a coloring? It's just taking the product of weights of all the tiles appearing in the graph. For example, you consider this particular tiling. So the tile of this form, the central node is yellow and the surrounding nodes are blue. So this kind of tile appear twice. So you multiply 2 twice. and for every other tile appearing in the graph, you multiply the corresponding weights. Okay, so it does not matter in which order you multiply, because all the examples, all the smearings that we consider here are all commutative smearing, so it does not matter. So you take the product of the weights of all the tiles that give you the weight of a coloring. Okay, now what is the weight assigned to the graph? You sum the weights of all possible colorings. So this is the weight assigned to a graph. So this is our model. Now to understand it a bit more, I will go through a quick example. And the example is to compute the clique number of a graph. So what is the clique number of a graph? It is the size of the biggest clique embedded inside the graph. So for this, so given this is an example graph, and we will represent this graph as a lower triangular adjacency matrix. So for example, the diagonal elements represent the nodes. And for example, here we have a 0. This is to indicate that there is no edge between A and C. Okay, there is no edge between A and C. And here we have a 1. This is to indicate that there is an edge between C and D. Between C and D, there is an edge. So like that, we have this adjacency matrix representation of an undirected graph. Now you have to find out the size of the maximum clique using such a weighted tiling system. For this, we will use 4 states or 4 colors. So every state can either have a horizontal line or not, similarly a vertical line or not. So this has both vertical and horizontal, this has not. So a coloring essentially will color the diagonal vertices by either by this plus kind of state or by this nothing state. Okay, and what it does is, if this originating vertex has a horizontal line, then the entire row will have the horizontal line. Okay, like here it has a horizontal line, so the entire row has a horizontal line. This one does not have a horizontal line, so the entire row does not have a horizontal line. Similarly, if this has a vertical line, then the entire column has a vertical line. This one does not, so the entire column does not have a vertical line. So roughly this corresponds to this diagonal vertices which are labeled with this plus corresponds to a subset of vertices that are being selected. And we want to check whether this subset actually forms a clique, for which we will check that for these internal nodes, every time you are labeling it with a plus kind of state, then it must be labeled with 1, basically meaning that there is an edge between those two. Okay, it should not be labeled with a 0. So this is the permitted tiles. And how do we assign weights for this? So this is a weighted tiling system over the max plus smearing. So we assign weights as follows. The diagonal vertices which get this plus state will get the weight 1, and all other vertices will get the weight 0. So the weight of this particular tiling will be the sum of these numbers, because in a max plus smearing, the sum is actually the smearing product. So we get 3. So this size of this subset that we have selected is 3. And the weight assigned to a graph is actually the max over all such colorings, which will actually give us the biggest clique embedded inside as we wanted. Okay, this is how this weighted tiling system works. Now, what is the problem that we are considering? We are looking at the evaluation problem and the complexity. So what exactly is the evaluation problem? We are given a weighted tiling system and a graph. And the question is, what is the weight that this particular weighted tiling system assigned to the given graph? Okay, we have shown that this problem is actually in a polynomial space. No matter which smearing you pick, we can solve it in polynomial space. We have considered particular smearings later, and then we have shown that it can. We have given optimal complexity for those cases as well. For example, if you consider natural smearing, this plus time smearing, this problem is actually sharp P complete. Okay, so sharp P is a class of a function is sharp P if there's a polynomial time Turing machine, such that the value of the function is exactly the number of accepting paths that the Turing machine has. So here the weights are given in binary. So this is the result that we have on max plus on natural smearing. And while we move to max plus smearing, this problem is P to the NP log complete. So it's a polynomial time. You have a polynomial time Turing machine that makes NP Oracle queries. And how many Oracle queries can it make? Logarithmically many in the size of the input. So it is complete for this class as well. In fact, the lower bound follows because the problem that we saw before, this computing the clique number, is already a p to the np log hard problem. Okay. And now we consider what happens for the bounded tree width case. In the case of bounded tree width, if the input graph has a bound on the tree width, which is fixed, then this problem can be solved in linear time in the size of the graph, and polynomial time in the size of the weighted tiling system. So this bounded tree width actually captures a wide variety of weighted systems studied in the literature, like weighted Mazurkiewicz traces or weighted nested pushdown systems or nested words under approximations of multi-pushdown systems, under approximations of message passing systems, etc. And with this result of ours, we get a uniform evaluation procedure for all these cases which are studied independently. So with this, I conclude. Thank you.
Thanks, Aishwarya. Are there any questions?
Maybe I have a question.
Yes.
It might be a little bit far. So what the next talk will be about games on multi-pushdown systems. So nested words is something I know. And what we were trying to figure out is whether there is a notion of alternation for graph automata. Do you know anything that could relate to this kind of computation model, which could capture a graph? However, it inflicts some kind of alternation in the graph structure. Like when we look at a nested word, for example, it is actually a run of a multi-pushdown system, which has some bounds. However, when we are looking at alternating multi-pushdown automata, it's not just simply a graph, right? So, I mean, it might be a little bit far, the question, so.
Yeah, so actually probably we can take this offline. We can talk then gather
Yes,
later
sure,
about
of
it.
course.
Actually, we have not in this one, but otherwise looked at what do I say, walking automaton kind of things on this, in which you have also a branching property which could relate to alternations. You can talk about for all paths and for some paths, etc., which can work on this kind of things. Yeah, but this one is a tiling. So tiling as such is not really. So the usual nested word automaton would correspond to the tiling automaton.
So are there any other questions? Okay, if not, maybe so I have a short. Yeah, go ahead.
No, sorry. Okay, maybe I'll ask my question. It's about this trick that you used of encoding a graph into its adjacency matrix, and actually you were tiling the adjacency matrix instead of the graph. And the question is, can you always do this trick, or does it cost you something? I mean, does it affect your results because you're tiling something different rather than the graph? That's more or less the question.
Yeah, so this is a very nice question. The thing is that we need a finite representation after all, and we cannot directly have a tile defined for arbitrary graphs, because the number of edges is, a number of neighbors is not bounded, and then we need how do I describe them? So for the moment, this model that we have is for finite degree edge labeled graphs, and then you have exactly one kind of edge for each type, like these trees or grids. And so this is also to showcase to you that actually it is not really limiting, because any arbitrary graph can be encoded via its adjacency matrix, and it is not really costing a lot. It's a polynomial time encoding anyway, because it's the number of cells that you have is exactly the number of edges that you n square. And you can define this automaton directly, or this tiling system directly on that. So it's not costing anything at the moment.
Okay, if there are no more questions, then let's thanks the speaker. Soren, can you share your screen?
I have.
Okay, yeah. Yeah. So the next speaker will be Soren, and he will talk about complexities of multi-pushdown games. So, over to you.
Okay, can you hear me?
Yes.
Okay,
Yes.
very good. So we're going to talk about multi-pushdown games and multi-pushdown, which are games on multi-pushdown system. And multi-pushdown system consists of a state space and a number of stacks and a transition relation for each stack. As with many concurrent models, the reachability problem is immediately undecidable, and the community so far has considered bounded multi-pushdown systems. And for that, we bound the number of the computations which are possible within the system. One computation looks like this. We have on the right side the stack contents, and on the left side we have a sequence of transitions, which is an interleaving of the stacks transition system. So a transition could be an internal transition which does not act on the stacks at all. It might be a popping transition which removes the top of stack symbol, a pushing transition introducing a new top of stack symbol, maybe another internal transition, another popping transition, and another internal transition. So this is the model we are working as.
So
yes?
yeah, I think we are not able to see your slides moving at least. We see some title slides, but we don't see your
this
slides.
This is not good.
Yeah, now we are able to see it. Yeah, thanks.
Yes, sadly, I cannot. Do you see this slide now?
Yeah. Thanks. Yeah.
And is it moving?
Oh
no.
I don't see anything.
No, it's not moving.
Yeah, this is not good. This is a problem indeed. Sorry, I'm not sure how to fix this then. Okay, let's hope it works with this. Can you see this?
Nothing yet. I see something, but can you make some moves so that at least I see your mouse moving?
Can you see the
No, I
mouse?
can't see anything.
Okay, then I'm sorry. I'm not sure whether I can fix this.
Could it be that you share the wrong screen? You're sharing a window, right? But not the full screen window, but the small window.
Okay, I can try that, yes. So can you see now?
Yes, we can see. Can you make some moves so that? Yeah.
Okay, very good. So as I said, for multi-pushdown systems, the reachability problem is undecidable, and a commutation works like this, where we have the interleaving of the threads, and we have pushing transitions and maybe popping transitions on the different stacks. We considered unapproximate executions, where we have bounds on the possible execution, and one bound is orderedness, where you have an ordering on the stacks, and a stack may only do a popping transition if all stacks of lower order are empty at the point of popping. So when we look at this example, now we have a popping transition on stack 2, and it is okay because stack 1 is empty. And if stack 1 pops, there's no stack of lower order. However, if the last transition would be on stack 2, this would not be a valid ordered computation, because at this point where stack 2 tries to make a popping transition, stack 1 is not empty. This is then decidable. And what we considered for multi-pushdown systems were games on these, which is occurring when we are trying to solve synthesis problems or trying to verify against branching time logics. Here we have the state space of the multi-pushdown system partitioned in Eve's and Anna's states and with priorities on the states. Then the game is played on the configuration graph as the arena where every node corresponds to a configuration. And the winning condition is a parity winning condition. And what we are trying to find is a winning strategy for Eve, which is just a subgraph of this graph where every node which belongs to Eve already has a predetermined move. Now, finding a winning strategy for players, of course, also undecidable unless we look at bounded place in such the game graph. And this is what we obtained results for. And as we can see here, we have for k-ordered stack multi-pushdowns, we already are at kx time for a fixed k, and for k as part of the input, we are non-elementary. Also for phase-bounded and context-bounded pushdown systems, we had a similar result. We're not the first to work here. There was a previous algorithm for phase-bounded multi-pushdown systems, which of course also carries over to context-bounded multi-pushdown system. Probably the most interesting result is that we could find that context-bounded pushdown systems are not much easier than phase-bounded multi-pushdown systems, where we only spare 2 exponents in the upper bound, and we could actually find a matching lower bound. The upper bound is obtained by simulating the game by a finite game, which instead of storing configurations with whole stack contents, only stores the top of stack symbols. However, such a simulating game which only stores the top of stack symbols cannot perform popping transitions. So the game ends up on a pop and one of the players wins. And for that, we need some additional information in our states. And also we need to make it possible in our game that we can simulate games which go beyond a pop. So technically, we arrive at a finite game by the use of summarization. And the idea is that if we look at the strategy for Eve, where every branch is a play of the multi-pushdown system, summarization looks at complete function calls and wants to capture the effect. So when we look at this, we have a push-pop pair, and the sequence in between, which is orange, we want to identify the effect of this sequence on the play. And when we look at the configurations, we immediately see that the stack contents have to be equal because we have a matching push-pop pair. And the only thing that actually changed is the state of the pushdown system. Notice that we only are looking at a single stock pushdown system currently. Now there's another effect, and that is the effect on the winning condition. The winning condition is interested in the maximum priority occurring infinitely often. So we also are interested in the maximum priority of the sequence because this is the effect the sequence has on the winning condition. And with that, we have a summary which captures this effect. And what we will see is that this set of all summaries is finite. When we look at this strategy, however, again, we know that when the push is happening, there might be many plays which actually eventually pop the pushed symbol. And even though there's possibly infinitely many popping situations, there's only a finite set of summaries, and therefore there's only a finite set of subset of the summary is possible behavior within Eve's strategy. And with this idea, we can transform the game into a finite game where we only store the top of stack symbol, where we assume we have simulated the game up to some pushing situation. And then we will do an intermediary move where Eve suggests any subset of the set of summaries. And then Anna can choose to pathfind by taking any summary in this set. And then we can continue the play as if we played the sequence in between. Of course, Anna might also have a strategy where she doesn't remove the symbol at all. And therefore, she can also pathfind to actually execute the push, forgetting the old top of stack symbol and memorizing the new one. This leads to a problem where we can actually run into a popping situation. And every popping situation has some kind of misbehavior of the player. Either Eve did not suggest the correct set of summaries, or Anna was wrong by pathfinding the wrong way. So what we want to do at the situation where we run into a popping situation, we would like to check against the proposed set of summaries. For that, we need to store it in our state at the moment we perform a push. Also, what we need to memorize is that we store in the summary the complete effect of the sequence. So what we also have in here is the maximum priority. And then the check becomes just looking at the state space, whether it is contained in a set of summaries. Now what we have done is we have transformed this to a finite game by storing the summary for the top of stack symbols and the set of summaries proposed for the top of stack symbol. And the size of this game is predominant by the sum by all these sets, because Eve has the choice of every such subset. And now for multi-pushdown systems, we want to do the same idea, and we will actually see that it works quite similar. So when we have a two-stack multi-pushdown, such a run is an interleaving of the two stacks. And first we want to look at the push-pop pair for the second stack. So we want to identify the effect, and what we will see is, of course, the second stack will be equal because we have a push-pop pair there. The first stack will be empty because we're in an ordered multi-pushdown system, and the first stack has to be empty during a pop of stack 2. And the only thing that changed apart from that is the state. So when we look at our summary, at the effect of the sequence, the first stack empties, the state changed, and we have the maximum priority. In the finite game, this looks quite similar to what we have seen for the single stack pushdown system. And the check actually amounts to only looking at the second stack here, because we know the first stack has to be empty. Now for the first stack, these summaries look different because the effect will be a different one. So when we look at the push-pop pair on the first stack, and we want to identify the effect, the first stack has to be equal because we have a push-pop pair on stack 1. However, the second stack does not have to be empty. Okay, so the first parts that, of course, are contained within the summary and are part of the effect is the state that has changed, and of course, again, the maximum priority during the sequence. However, now we can have that the second stack has also a push-pop pair, which prolongs, which goes beyond the pop on stack 1. And therefore, what we also have to see there is that the top of stack symbol for stack 2 has changed. So this is part of the effect. And now we want to we want to be able to skip the push-pop pair on stack 1 and the complete sequence. And our finite game, however, contains the information for the top of stack symbols of proposed summaries and of the maximum priority seen so far. So we need to contain this information for the push on stack 2 as well. So we need to identify the maximum priority since the push of stack 2 in the sequence. And we need to identify a set of summaries that was proposed by Eve. And what comes to mind as such a set of summary is the same principle as we had before. We identify all the runs that are possible from the push on stack 2 and find the pop-saying situations which are conform with Eve's strategy. However, this is not quite correct because we already fixed the sequence up to the pop on stack 1. So what we will gain is a subset of this previous mentioned set. And with that, we have the set of all summaries which are possible for stack 1 push-pop pairs. Okay, also here we have the finite game. It also looks similar. And when we run into a popping situation, we will check for all the parts that are within the summary. So we will identify the state. We will identify the maximum priority seen for both of the top of stack symbols. We will identify the top of stack symbol from stack 2, and we will check whether there is a summary in S1 that matches this. However, for the set of summaries for stack 2, which are part of the summary, we are not taking S2, because when we remember this picture, what we are actually looking for is a subset of the set S2, which is proposed. Okay, I'm not sure how the time is.
Maybe 1 or 2 minutes.
1 or 2 minutes. Okay, maybe I can do the lower bound in that time. Okay, so what we did for the lower bound is we had a reduction from alternating Turing machines. And when we look at this, the main challenge is that configurations of Turing machines, of these Turing machines, are very, very large, and namely k-2 exponential in the input size of the word W. However, the multi-pushdown game has to stay polynomially sized. And what does such a Turing machine do upon an input W? Well, it computes a computation. It tries to find a computation tree. And this is very similar to finding a strategy in a multi-pushdown game, except that the configurations do not match. So what we do instead is we hide the Turing machine configurations within multi-pushdown configurations. We do this by identifying a single stack, which will have the task of representing these Turing machine configurations. And on top of the stack, there will always be a configuration. And then we have modeled the initial configuration. Because it is a universal branching state, Eve will be the one to choose a Turing machine transition. And then the game makes sure to push the corresponding configuration. And we have simulated one step. We continue this. And as that, we will run down a branch of the Turing machine computation tree. Now let's have a look in a little bit more detail how this actually can work. Well, choosing a Turing machine transition can be done using the state space. This is not very hard. And afterwards, the hard part is pushing the correct configuration, because when we remember, these configurations are very long. And instead, what we do is we don't use the state space to execute this, because we can't. Instead, we let just Eve push any sequence in the hopes that she pushes actually the resulting configuration. And afterwards, we have to check that actually the pushed sequence is a Turing machine configuration at all, and that it is actually the resulting Turing machine configuration from before. The first part is mainly only checking the length of the sequence, and the second part amounts to checking a relation. Technically, in order to do this check, we have to compare single positions in the two words, and still the words are very long, so we can't do this using the state space. Instead, we index the configurations by postponing every letter with a binary representation of its position. And then comparing two Turing machine configurations for being equal, instead what we have to do is we have to compare the indices. And the indices are one exponential smaller than the total configurations. And because they are still too large, we actually will inductively apply this principle, and we will arrive at multi-layered indexings in order to arrive at a polynomial level long index at the lowest level. And then instead of storing only the configurations, we store these indexings on our stack, and the tests become upon indexed word. And we need to check certain relations on here. So the first one we already saw is the Turing machine configurations. Now for the indices, we also need to check equality. We also need to check that the topmost sequence is actually a valid indexing, which amounts itself on checking certain relations on the indexing words. And what we do technically to simplify this proof and not show this for every relation itself is we introduce first order relations, which is relations among words of same length. And the idea is that we represent this relation by a formula, and the words are related if and only if they are a model of the formula. And such a formula looks like this, where we have the quantifiers looking similar to first order logic, quantifying over the set of positions, and where we have a function symbol, which is transforming a position to the symbol in the word. And with this idea, we can identify what this formula actually means. It is on an alphabet of 0 and 1. It is a formula for the relation less than on binary encoded words. Okay, and with this, we can simplify the proof by only showing that for any first order relation, there is a multi-pushdown system which actually checks this relation. And that is all we have today.
So maybe we have, yeah, thanks, Soren. Maybe we have time for one quick question. Okay, if not, let's thank the speaker. Sven, can you share your screen?
I try, yeah. So maybe I should check that it moves. It does, right?
Not really. I see. Yeah, it does. Yes. Thanks. Yeah, so now we'll have Sven presenting to us about Nivert theorem and logics for weighted push-down automatic. Over to you, Sven.
Yeah, thank you. So I'm Sven Schwentick from Leipzig University, and I'm presenting work together with Manfred Droste, also from Leipzig, and Werner Kurich from Vienna. So we were looking into a logical characterization for this class of languages. So we are talking about context-free languages of infinite words. So this is omega context-free languages. And we're looking at the quantitative, or also called weighted setting. We have other results like this Nivert theorem, but I will looking into this logic mostly. So for this short talk, I will dive directly into the logic, which is decomposed out of several aspects. So the first is monadic second order logic, which is the classical logic equivalent to regular languages. And of course, you have to extend it. And the idea for the context-free logic comes from Lautemann, Schwentick, Thérien. They did this for the unweighted setting and finite words. And here, this is already extended to infinite words. So sigma omega will be infinite words over sigma. And we are talking about the matching relation, which is a relation on the positions in the infinite words, so the natural numbers. And we call such a relation matching if it fulfills three properties. It has to be compatible with the smaller relation. So this is actually a counterexample. And we don't want to have a position related to two other positions. So at most one matching relation per position is allowed. And last but not least, we don't want it to be crossing. And what you get then is something like this, where you can actually see that it behaves a little bit like Duck languages. So you have like opening brackets here, and you have closing brackets here. And I guess this is actually the idea. And now we can take this relation and put it out into our logic. So then we have this matching relation mu here, and we can put two positions x and y into a relation, which means that one will be pushing and the other one will be popping, or that we just want to make sure that their amount is equal or something like this. So then we get something that is a context-free language, and we add a second layer that can talk about weights, which I don't want to go into detail here too much. So we will be using an omega valuation monoid for the weight structure, which I guess is something like a generalization of complete simmering. So we need the completeness property here because we're talking about infinite words. And we have something like that gives us, if the formula beta from the first layer, so it's a Boolean formula, unweighted formula is valid, then we have the following weight. Okay, and of course then the matching variable mu is unbounded. So we add a third layer which bounds our matching variable existentially. So this is some kind of quantification where we actually add up all possibilities for mu and of the formula phi from the second layer. So this is our logic that we proposed, and we prove that it's equivalent to our language class. And we do this by using two main ingredients. So the first is, if you look at the first two layers of our logic, then this is actually equivalent to nested omega word automata. Because now, of course, mu is no longer bounded, so it occurs freely in our logic. And if we want to cope with this, then we have to encode it into our word. And what you then get is a word together with a matching variable, like a matching relation. And this is nothing else than a nested word. And we can apply a result from Droste and Duc, who tell us that this logic is actually equivalent to regular nested word languages in the weighted case and also for infinite words. And then the only thing that is missing is the quantification, which is nothing else than a projection from nested word automata to push-down automata. And this projection is interesting because those nested word automata from Droste and Duc are actually Mahler accepting, and ours are Büchi accepting. So we proved that those two acceptance properties are actually equivalent. And what you get then is a push-down automaton with very specific properties. And this property is something like a normal form, which is interesting to know. So we call this a simple push-down automaton. And yeah, if you look into your memory, you have some picture of a push-down automaton, which is some finite state. You have finitely many states and a push-down stack to store information. Of course, you have an input tape. This one here is infinitely long. And for our proof, it makes sense to restrict this automaton and to say, okay, epsilon transitions make a problem for our proof. So let's look at real-time. Well, they're called real-time push-down automata without epsilon transitions. And instead of taking the normal approach where you access the stack, where you always pop the topmost letter and replace it by a word, which can also be the anti-word, instead we will take only 3 stack commands like in the nested word automaton as well. You will have pop a letter A, push a letter A, or ignore the stack. And in the last 2 cases where you push or ignore the stack, you actually also don't know what is on top of the stack. So you don't have in every transition that you know what is currently the topmost symbol. And yeah, as I said, we call this automaton model then the simple push-down automaton, which works in the unweighted case and is equivalent to the normal push-down automata, and also for infinite words. And I only found it once in the literature in a class in a proof by Plas and Gurevich. So this was on nested words, and I find it interesting that it occurs only there. So it seems that this is a quite natural normal form for push-down automata, which can be helpful also for other proofs. And for our proof, it is necessary because our logic can only do these stack commands, so to say. So the matching relation only fits to those stack commands. So yeah. So if you have this automaton, then you can easily, or not easily, but you can prove that the class accepted by this automaton model is equivalent to our logic. So I summarize. We have a Niva-like theorem that I haven't talked about. So this is some kind of a decomposition theorem, which is inspired by Maurice Niva, who actually has something like this for a decomposition of transducers. And we have this equivalence of Büchi and Mahler acceptance, which we also use for our logical characterization, which basically tells us that if we take this logic that I gave you an idea of, and we have to restrict it a little such that we get an equivalence, an expressive equivalence of this logic and those simple push-down automata. Yeah, this is basically the idea of the paper. Thank you for listening.
Thank you, sir. Are there questions? So if not, maybe I have a small question. Do you have an effective translation of one into the other, given a push-down automata to get a logic? And if so, have you studied how much time does it take for this translation?
For translation from push-down automata to the simple model?
Yes.
This was the question, right? So it depends. If you have a push-down automaton which is not simple and has epsilon transitions, then the only way that I know of to get rid of these epsilon transitions is to translate it into a grammar in Kreibach normal form, which is not very fast. I don't know exactly.
It's probably the reason why it has not been. Do you think so, or I'm not sure? Maybe,
yeah. But there's actually lots of applications where you use push-down automata without epsilon transitions. So there is a lot of literature about push-down automata that are real-time. So these epsilon transitions, to get rid of them is actually a normal thing. But then the normal translation from the Kreibach normal form to push-down automata gets you a push-down automaton with only one state. And instead, our construction will give you a simple push-down automata with one state per non-terminal in the grammar. So this is a different construction, and it's not slower than the normal construction if you have the Kreibach normal form already.
Okay. Mm-hmm.
So if the push-down automaton is already real-time, then it's easy, and otherwise it's slow.
Okay. Okay. Yeah. Are there any more questions? If not, let's thank the speaker.
Thanks.
Balasubramaniam, can you share your screen?
Yes, just a minute.
And Sven, of course.
Okay, I'll just okay. Can you see it?
Yeah, maybe you can move around so that.
Yeah. Can you?
Perfect.
Okay.
Yeah.
Okay. Great. So I'll start. Okay. Thanks for having me here. So today I'll be giving a brief talk on the parameterized complexity of safety of threshold automata. And to introduce threshold automata, I'll use the same example that I used in the main presentation. So threshold automata are a formalism for specifying distributed protocols in which each process is running the same each process is identical and is running the same protocol template. So in a threshold automata, we can specify a protocol template by means of specifying states and then by means of specifying transitions between these states. These transitions are labeled by some labels, but just for the moment, let's ignore the labels and look at what this template allows a process to do. So a process can start in any one of these two initial states, and then it can either crash, that is move to this crash state from any of these two states, or it can move to the send state, and then from the send state, it can either move to the attack state or the retreat state. However, threshold automata allows us to do much more than just specifying the process template for a process. For example, each threshold automaton usually has a condition which we call the resilience condition. So very roughly, the resilience condition allows us to specify variables, which we'll call the environment variables. And each environment variable will stand for a total number of some type of process executing this template. So for example, here, N will denote the total number of processes executing this protocol, whereas T will denote the total number of processes executing this protocol, which will crash, that is move to this crash state. And this condition N bigger than 2T just says that the number of processes which are not going to crash, which is N minus T, is bigger than the number of processes which are going to crash. This resilience condition allows us to only focus on those configurations which satisfy this constraint. Another feature of threshold automaton is the notion of a shared variable increment. So threshold automata allows us to specify shared variables, that is variables which are shared among all the processes and can be accessed by all the processes. And a process can increment a shared variable when it takes a transition. So for example, if a process is moving from this state to this send state, then it can increment this shared variable add. Similarly, if a process is taking this transition, it can increment a shared variable re, and so on. And finally, we have the important notion of a threshold guard. So in a threshold guard, a process can compare the current value of some shared variable with an affine linear combination of the environment variables that I had introduced in the resilience condition. So let's, for example, assume that a process wants to move from the send state to the attack state using this transition. First, it checks that the current value of the shared variable at is bigger than or equal to n minus t. And it also checks that the current value of the shared variable f is bigger than or equal to t. Only if these two conditions are true, then a process can take this transition and move from the send state to the attack state. So this roughly constitutes the main features of a threshold automaton. And let's move on to the sort of questions that we are interested in regarding this. So in this paper, we are mainly concerned about safety verification problems for threshold automata. That is, we are given a threshold automaton, and we are given two sets of states, which I'll call the specification. And what we would like to verify is whether there exists some population size n, such that running n copies of this threshold automaton in parallel, that is letting n process run this threshold automaton, will ever reach a configuration which puts at least one process in the states in this set, and exactly zero process in the state in this in each of the states in this set. And it is known that this problem, the safety verification problem, is NP complete. And what we try to do in the paper is as follows. So we try to find parameters of the input, which are usually small in practice. That is, so for example, the size of the resilience condition, it has been empirically determined that the size of the resilience condition is much smaller than the size of the protocol template in itself, roughly on the order of, let's say, 5 or 10 or something. And so the size of the resilience condition constitutes a potential parameter of the input. And in this paper, we try to find other parameters of the input, which are usually small in practice. And we try to find fixed parameter tractable FPT algorithms. That is, algorithms whose running time is of the form f of k times a polynomial in the input size, where this function f solely depends on the parameter k. The hope is that if the parameter k is small and the function f is moderately exponential, then we can still hope to solve this problem in practice. Alas, our first result is a negative result, which shows that the safety verification problem for threshold automata parameterized by these parameters is W1 hard. So this denotes a total number of guards appearing in the threshold automaton, and this symbol denotes the size of the resilience condition. This symbol denotes the size of the specification, which, as you may recall, is just the size of these two sets. And this is just a maximum constant appearing in any of the guards of the threshold automaton. So we show that the safety verification problem parameterized by these 4 parameters is W1 hard, and W1 hardness is just is roughly a parameterized equivalent of NP hardness. And we complement this negative result by giving 2 positive results for subclasses of threshold automata. In our first result, we show that for acyclic threshold automata, that is threshold automata with an acyclic control structure, the safety verification problem parameterized by these 4 parameters, along with the length of the longest path in the protocol template, is fixed parameter tractable. And the second and the more important result is that we identify a class of threshold automata, which we call multiplicative threshold automata with constantly many fall guards. And for this class, we show that when parameterized by the number of guards appearing in the threshold automaton, there is an FPT algorithm, right? And the main idea behind the last result is as follows. So instead of attacking the safety problem directly, we first propose a restricted form of the safety problem, which I've defined in detail in the main presentation. And we show that for multiplicative automata, this restricted form of the safety problem reduces to reachability in continuous petrinets. And it is known that reachability in continuous petrinets can be solved in polynomial time. Hence, this restricted form of the safety problem for multiplicative automata can also be solved in polynomial time. And then what we do is we use existing results on threshold automata to show the following. So very roughly, we show that solving the safety problem for multiplicative automata can be accomplished by solving these many restricted safety problems, where this G is just a number of distinct guards as before, R is the number of transitions appearing in the threshold automaton, and GF is the number of fall guards appearing in the threshold automaton. So here a fall guard is just a threshold guard which has a less than symbol in it, right? And then notice that if GF is constant, then this expression is of the form f of g times a fixed polynomial in R, where f is a function which solely depends on g. And we have already shown that solving restricted safety can be done in polynomial time. Hence, if GF is constant, then the total time taken is of this form, which is fixed parameter tractable when parameterized by a number of guards. And we implemented the algorithm that you have described in this paper and compared it with the algorithm used to prove inclusion in NP and also with BIMC, which is a state-of-the-art model checker for verifying properties in threshold automata. So the threshold automata here are taken from a popular benchmark of various threshold automata, which by themselves were obtained by encoding various distributed algorithms from the literature in a form of threshold automaton. And we observed that many of the threshold automata in this benchmark are multiplicative and have at most 1 or 2 fault guards. Hence, we are able to implement the algorithm in this paper on those threshold automata. And we see that there is no clear winner in the sense that there are threshold automata in which the algorithm in this paper performs worse, and then there are threshold automata in which the algorithm in this paper performs better than both the other algorithms. Thank you for your attention, and I'll be happy to take any questions.
Thank you, Balasubramanian. Are there any questions? Okay, if not, I have 2 questions. So, in one of your parameter was acyclicity in
here, yes. One of the cases, yes, yeah.
Yes. So, does this not work for bounded tree width, for instance? Have you already considered this?
So you mean with these parameters?
Yeah.
Okay, so here I'm parameterizing by the length of the longest path in the control structure.
Okay.
Right?
Okay.
So
okay.
I mean, this diameter represents the diameter of the graph, and yeah, I mean Then if we are talking about bounded tree width, then we would, I guess, have to talk about diameter in the tree width, or the tree width representation, I guess. I'm not.
You might have loops and.
Okay. Yeah. Yes.
Okay. Can you go to your experiments?
Yes.
Another question is, since you have, there is no clear winner, does this also automatically mean that there are more parameters hidden parameters which could give you better algorithms, or?
Probably. So I mean, what I did mention is that, okay, so very roughly the algorithms that the algorithm in this paper performs worse, which are which, if you think, was somewhere around here, are threshold automata in which the number of locations is rather small. I mean, the threshold automata in these the states in the threshold automata are rather small. These automata have states roughly, I think, 20 or 25 or something. But whereas as you go below the table, the number of states increases. The states here, I think, correspond to 3,000 or something. So okay. I think for small inputs, our algorithm is worse, but I think for bigger inputs, it's better.
So are there any other questions? If not, let's thank the speaker. And
thank you.
Thanks all of you for attending this session. Yeah, so I think there is the gather session that you could all socialize and come back for the next session. Thanks all of you.
Hello, sir. Bhaskar here. Hello, Suresh.
Yes, I have unmuted myself. Yes.
Yeah, so that it's 4:45. You can start.
Okay, I can start. Okay. So should I wait for some more people to turn up or?
A few more minutes we can wait, perhaps.
I'll wait for a minute or so.
Yeah, maybe 1 minute is fine because they might be on gather. They might just come.
Sunil, what are you saying?
Maybe we can wait for a minute. They might be on gather. They might just come in. People might.
Okay, sure. We'll wait. Yes. So meanwhile, maybe we can set up the screen for the first speaker. Dominic, who will give the first talk? Dominic?
No, it will be me, Andrew.
Hi.
Hi.
This is, yes, so you can maybe share your screen already.
Yes, please allow it. Says it.
After, can you allow it? Yes, you are the co-host. You've been made the co-host.
Yeah. Okay.
Okay, so we'll wait for a minute and then I'll start.
Yeah.
So I think each talk is supposed to last 15 minutes, but we have 15 more minutes extra. So maybe we can go a couple of minutes extra. So there are only 4 talks and this session is an hour and 15 minutes. So there is some wiggle room for us. Okay, I think we can start. It is 4:47. Sunil, can we start?
Okay,
yes.
Thank you.
Let's start.
Yeah, let's start. So welcome everyone to the second session on day 2, second session in Track B. We have a slate of very nice talks in this session. The first talk is a paper by Dominique Perrin and Andrew Rizzico, the degree of a finite set of words. Andrew will be giving the talk. Over to Andrew.
Thank you. So yes, I will talk about the degree of a finite set of words. So let me first start with some motivating definitions. We're considering finite sets of finite words everywhere in the talk. And so a word is called synchronizing for a set X if for any words U and V such that the whole concatenation UWV is in X star. We also have that UW and WV are in X star. So a set having a synchronizing word is also called synchronizing. The motivation for this definition is in particular such that if we see a word WW somewhere in a concatenation of words from X, then we can partition this long concatenation into shorter ones, and then we can decode these shorter concatenations over X in parallel completely independently. So mostly synchronizing words have been considered for codes. A code is just a set of words such that there is no double factorization over this set of words of any word from over the same alphabet. So for example, ABA is a code, but ABBA is not a code since we have a double factorization of the word ABABA. Now to find some way of representing a set of words as a composition of possibly simpler set of words, we define the notion of a composition for arbitrary set of words. So essentially, the intuition is that we take a set X of words, and then we write it over not its initial alphabet, but some alphabet consisting of words from another set Z instead of just the alphabet. So
This way, a composition is just some mapping from the alphabet of Y to the set Z. So we require them to be of the same size. And so if we have X to be a composition of Y and Z, then we call Y composition Z a decomposition of X. So for example, if we have the sets Y and Z as you can see on the slide, then their composition under the mapping sending U to A, V to AB, and W to BA is a set A, ABA. And we have to restrict our compositions a little bit by considering trim decompositions and trim compositions. So it does not actually restrict us much. And the idea is that we should obtain every word of X uniquely from words from Y. So in our example, the decomposition is not trim, since we can obtain the word ABA in two different ways by taking UW. So we go then to A and BA, or by taking VU, we then take AB and then A. So in this case, the decomposition is not trim. And in general, if we take an arbitrary decomposition of a finite set of words, then we can make this decomposition trim just by removing some words from Y, and then we remove some words from Z. So in our case, we can remove the word VU from Y, and then we have to remove AB because it corresponds to a letter which is no longer used in Y. And finally, another definition is of a complete set, and a set of words is called complete if for any word over the same alphabet, if any word over the same alphabet is a factor of a word in X star. So for example, you can see set A, BA, BB, which is complete, but the set A, ABA is not complete since we cannot see BB in any concatenation of words from this set. So the idea of our work is as follows. We have a decomposition of a set, a trim decomposition of a set X, of a finite set X into sets Y and Z, where Y is complete. And we want to define some number which is called the degree of X in such a way that, first of all, the degree of X is 1 if and only if the set is synchronizing. And second, the degree of X is at most the degree of Y times the degree of Z. This is already known for the case of codes. And in the case of codes, we actually have equality instead of inequality. But in our case, sometimes we have a strict inequality here. So the idea of showing that and defining the degree is first we need to find an appropriate class of automata. So in our case, we're looking at automata recognizing X star with multiplicities for a finite set X. So we take our sets Y and Z and we introduce flower automata of these finite sets. We show that they indeed recognize these sets with so Y star and Z star with the multiplicities. And then we define a composition of this automata in such a way that the resultant automata multiplicities. So then to actually multiplicities. So then to actually define the degree of a set, we look at the action of a permutation group from the transition monoid of this automaton. So we look at the action of this group on strongly connected components of fixed points of idempotence. So here we can see the action of a particular word in the alphabet, oh sorry, in the automaton of X. And so we see here that there is only one strongly connected. So we have two fixed points, 1 and 8. And so we can see that there is only one strongly connected component in this case, but one can imagine that there are more than one. Then we have some non-trivial permutation group acting on that. And the order of this permutation group is actually the degree of a finite set X. And then since we have this nice relation between automata and sets of words, and since we have compositions defined properly for both sets and automata, we can look at the relations between the groups of X, Y, and Z, and show that actually what we have is the inequality we were looking for. And we also show that if the degree is 1, then the set is synchronizing. So that's it. Thank you.
Thank you, Andrew. Are there any questions? Any questions, please? So let's thank Andrew again. Let's move on to the next question. Let's move on to the next talk. The next talk is by Pavel Paris, higher order non-determinism step by step.
Yes, okay. Welcome to my talk. I will present my paper, which is titled Higher Order Non-Emptiness Step by Step. I'm from University of Warsaw, Poland. Okay, so what is this paper about? So the title has 3 components, and this is about higher order recursion schemes. So higher order recursion schemes, this is a generalization of context-free languages, so they describe some recursion where you can have higher order functions, yes, so functions that take other functions as parameters. Now we have non-emptiness, which is so either we can see it as like just simply language non-emptiness, or equivalently, this is about acceptance problem for alternating reachability automata. And this step by step is a description of my method, which is a new method which works in multiple simple steps. Okay, so here I have the problem which I solve. This model checking problem for recursion schemes. Yes, so on the input we have 2 things. One thing is an alternating tree automaton. So it's just an automaton that reads an infinite tree and either accepts or rejects. And we have a recursion scheme, which is some model for that describes an infinite tree in a finite way. And the question is whether this automaton accepts the tree described by this recursion scheme. And it's known for a long time that this problem is decidable, even for parity automata. So for MSO, yes, for regular languages over trees. So we can check whether this tree belongs to some regular language. And there are several proofs already, several algorithms using different techniques. And in this paper, I show a very simple algorithm, but only for reachability automata, not for all parity automata, but only for reachability, which is a strict subset. Yes, it defines only some of regular languages. And my algorithm achieves the best complexity known so far. So this problem is quite complex. It is an n-fold exponential time for recursion schemes of order n. So there is these recursion schemes, they can be parameterized by some order, by something that is called an order, which is essentially the nesting order. Yeah, so order 1, these are just standard functions, and order 2, these are functions that take other functions as parameters, and so on. Yeah, so this is nesting of these functions, and we also know that this is a fixed parameter tractable. So this should be FPT, not FTP. Fixed parameter tractable. More precisely, it's linear in the size of this recursion scheme, and it's only in the size of the automaton and in the maximal arity of types appearing in G. Yes, so type meaning number of parameters. So you can have many functions, many procedures there, but yeah, only the number of parameters of a single procedure is the thing that goes to the exponent, and the size of the automaton as well. And this is two things that are known both for parity automata and for reachability automata. So in particular, already for reachability automata, the problem is n-fold exponential, nx time hard. And yeah, and as written here, I give a new algorithm doing the same, and this algorithm works step by step, meaning we have the original recursion scheme Gn, which is simplified. So there, I give a translation that translates this recursion scheme of order n into an equivalent recursion scheme which is of order n-1, meaning simpler, but the size grows exponentially. So if we repeat this, we get a recursion scheme of order 0, which is simply does an automaton. Yeah, it does recursive equation for the. So we basically we get a regular tree at the end, and for a regular tree the problem becomes trivial. And here I have the idea of the transformation. So we assume here that there is some procedure k of order 1, meaning that it takes some argument which simply generates a tree. Yes, so L is some tree, or L is some procedure that generates some infinite tree, and this tree is taken by k and used to generate some larger tree. Yes, so it can be used only in this way as drawn here. So it can be attached in some places. So essentially, k generates some context, yes, some part of the tree, and L is attached below. And now, when such a tree can be accepting, so either this witnessing run uses only this k fragment, this top fragment, and doesn't go to L at all. Yeah, so this is this red possibility on the left. And the second possibility is this blue possibility, where we use this L. And now the idea of this transformation is that we generate this tree on the right instead of this KL. So instead of putting this L below K, we put it on the side. So we generate two variants of K. In one variant, we put this bottom as every argument, meaning that we cannot go there. This is rejecting always. And in the second variant of K, we put top, which means that this going to this argument is immediately accepting. And here we create this or and and. So when such thing can be accepted, so either we can go left and use only this k without going to the argument. Yeah, this corresponds to this this red possibility before, and another possibility is to go right, and here both things have to be accepting because this is AND conjunction. Okay, so we have to be accepting inside L. We're going to the argument immediately accepting, and additionally this L has to be accepting as well, meaning yeah, we have to go here and we have to accept here. So instead of so this kind of application is replaced by some alternation here, but the order of the whole thing decreases by 1. Yes, because here we had some k was a procedure taking some argument. Now we have this k this bottom which generates simply a tree, but the size grows, yeah, because we have two variants of this k. When this k has more arguments, we need more variants. So exponentially many in general, yeah. If we have n arguments, then we have for each of the argument, we can either substitute bottom or top. So this grows exponentially, but now k is not a procedure; it's just an order 0 thing which simply generates a tree. So this is the idea of the transformation. And this is applied everywhere in the recursion scheme, and yeah, you can see on the full video how it works in more details or in the paper. So basically that's all. Yes. So as to summarize, we consider the model checking problem for recursion schemes versus reachability automata, alternating automata. And we propose a new method, which is a new algorithm, which is simpler than the previous algorithm solving this problem. The simplicity is mainly achieved because we instead of doing everything in a single step and working with these higher order functions, we repeatedly reduce the order of the recursion scheme by 1, and this increases the size exponentially. This way we obtain optimal complexity. And as a future work, I have listed here 2 things. So to extend this method, first to parity automata, to add parities there, and second thing is so-called diagonal problem or simultaneous unboundedness problem. This is also a problem which is already solved for recursion schemes in some complex way, but it seems that a similar method, similar order reduction may also simplify the algorithm for this more complex problem. Yes, so yeah, basically that's it. Thank you.
Yeah, let's thank Pavel for a very nice talk. Are there any questions? Anyone?
Maybe one.
Yeah.
From the classical FBT point of view, as Pavel mentioned it. So what happens, you have obviously FBT results if you have 2 parameters, size of the automata and arity bounded, if I got it right. What happens if you bound only one of the 2? Is this then W hard in some sense, or even para NP hard or something like that?
So I don't understand. So basically, this is parameterized by the product of these 2 parameters. Yes. So
yes.
So
but of course you can consider single parameters like only arity or only size of the automata.
Yes. So then it's yeah. If you fix only one of them, it doesn't help you. Yes. It's.
So it's still very hard, so to speak, right?
Yes.
Okay, fine.
Yeah, because essentially you can make a trade-off, so you can always kind of make a product of this recursion scheme with this automaton, and then the automaton becomes trivial, but the arity of these procedures grows. Yes.
Okay,
so
I see.
Actually, the real parameter that you have is a product of the size of the automaton times the number of parameters. Yeah, number of arguments of the functions.
Okay. Thanks.
Are there any other questions? I have a question. So why does this identity hold the KL, especially in the K through L decomposition? So why is it that all these paths inside L are uniform no matter where you touch them from K?
So the point is that L is a fixed tree. Yes, it's used multiple times, but it's the same tree. Yes, so if you have here an accepting run, it can be the same in each of these copies of L. Yeah, so if you start with an arbitrary run, there may be different. You can always choose just one of them. Yeah.
Okay. So another question is, you said in future work you would like to extend it to parity. Right now, are there any other conditions to which you can, any other things beyond reachability that you can, that the same technique will extend to, or is it only reachability?
So this is only for reachability. Yes. So for parity, I almost have it. Yes. So here you have to add some priorities. So it seems that it can be done very similarly. Just instead of one copy here, you need many copies, one for each priority of the parity condition, and then you put this priority on this edge here going to L. Yeah. So instead of going through this tree with the highest priority something, okay, yeah, you put this priority here, something like that. Yeah.
Right. Are there any other questions? If not, let's thank Pavel again.
Yeah, thank you.
Okay, thanks a lot. So the next talk is by Petra Wolf, synchronization under dynamic constraints.
Yeah, thank you very much. Can you see my slide?
Yes, we can see your slides.
So I will talk about synchronization under dynamic constraints. And this goes back to the original motivation for synchronizing automata by creating parts orienters introduced by Thérien in the 1980s. So parts orienters are, in the setting of parts orienters, you have an assembly line and you have some parts coming in with an unknown orientation. And you don't have any observers which can tell you the orientation of your parts because they're very expensive. Instead, you want to find a sequence of modifiers like jumps here or walls against which your object slides in order to bring your part from an unknown orientation in a well-defined orientation. And this was modeled as synchronizing finite automata. So the different orientations are modeled as states of an automaton, and the modifiers, such as a jump, is modeled as letters. And hence finding a sequence of modifiers which brings the part from an initial unknown orientation into a well-defined orientation corresponds to finding a sequence of letters which map every state of the automaton into one single state. And in this model here, it is assumed that the different modifiers don't have any impact on the part apart from changing the orientation. So for instance, it does not matter in which sequence you orient the parts. It's not like your part is deformed after applying a modifier. But this does not really reflect reality. For instance, if your part is a box with lids, which can be opened or closed, then if you rotate the box, this will have an impact on the object itself, as for instance, the lids can open or close. So if you now rotate the box, then the lids fall open. And if you might want that in the end, you're in an orientation where the box is facing upwards and the lids are closed, then you have to close the lids again. But this does not prevent us from opening them again with an effect of another modifier. So instead of encoding that whenever we're in a state where the box is facing downwards, we have to reach the state where the lids are closed. Again, we want to encode that after the last time the box was in the state facing sidewards, it needs to visit the state lid closed at least once. So what we're doing here now is we're comparing the last times a state is active. So the last time the automaton is in some state P versus the last time the automaton is in some state Q. So in a sense, this version here models positive constraints for the future in a sense that whenever I reach the state P, I have to later reach the state Q. But we could also encode negative constraints in the sense that whenever I reach a state P, I can no longer reach the state Q. And this can be motivated by this example that you have, again, a box with some lids, and you have a mechanism keeping the box closed. And you want to end up in an orientation where the box is open, but so this closing mechanism is removed, but the lids are still closed and the content of the box is still in it. And then you're not allowed to rotate the box after you opened this mechanism. So for instance, if you would open this mechanism and you would later rotate the box, then the content would fall out and you could not reach your final orientation anymore because the content of your box is lost. So what we encode here is as soon as the state where the lid is open has been reached, the state where the box is facing sideways should never be entered again. And with this motivation in mind, we defined different ways in which BERT can induce an order on the states by comparing the last occurrences of states with each other, or by comparing, like in the second example, the last position of a state with a first position of a state, in a sense that whenever I reach some state, I'm not allowed to reach some other state anymore. And we also distinguish whether we want to compare the states in a sense that we are looking at whether they appear as an active state in the set of active states, or whether we track the active states on their single pass. So the difference is whether we are looking at the set of active states and look which states appear in the set of active states, no matter from which path they come, or whether we track individual paths. And this is indicated by an S for set and a P for path. And then we define the synchronization under order problem variant for each of these introduced orders, where we are given a deterministic complete automaton and a binary relation on the set of states. And the question is whether there exists a synchronizing word that maps all states of the automaton to one single state, such that the input relation agrees with the order induced by the synchronizing word. And we also consider the subset variant, where we don't ask for the whole set of states to be synchronized, but only for a subset of states. And in the last variant, for the version where we formulate negative constraints for the future, where we forbid future state visits depending on which state we already visited, we also considered the variant where the input relation is a total order, because then this problem here is equivalent to synchronizing partial weakly acyclic automata. And finally, I want to show a summary of our results. So what I not mentioned so far is that we also differentiated whether we take the initial configuration into account or not. Because, for instance, when we consider individual paths, and then we have some states which do not appear on the path at all, then if we would say that we ignore the first position, so we ignore not appearing states at all, and only consider the actions of our words, then we observe the different behavior as if we say that, okay, states which do not occur at all must be taken into account as well. And then we looked at the complexity of the problem, and we noticed that if we tracked states on individual paths rather than only looking at the set of active states, the problem in some cases becomes easier. For instance, if in the first example where we strictly compare the last occurrences of states, we drop down from being p-space complete to being contained in NP. And for the negative constraint version, where the order is total, we also observed a difference here, whether we take the initial situation into account, because in this initial situation here, the problem is equivalent to synchronizing partial weakly acyclic automaton, whereas if we ignore the initial configuration, then it's closely related to subset synchronization of weakly acyclic automata. And we observed that if the input relation is a total order, the problem can become significantly easier than if we just allow an arbitrary input relation. And if we move to the subset synchronization problem, all of the variants become harder, and we can only observe a drop in complexity from being p-space complete to NP complete if the input relation is total. So thank you very much. Do you have any questions?
Yeah, thanks a lot, Petra. Are there any questions?
I have two questions, if I may.
Yeah.
So, is there any relation with the constraint synchronization problem when you're allowed to take synchronizing words only from particular language?
No, this is a more dynamic problem than the static constraint synchronization problem, because in the static constraint synchronization, you just say my word needs to be from this constraint language. But here, the letters which are allowed are more of a dynamic behavior because they depend on your history of visited states.
Mm-hmm. And thank you. And second question, so I think in the paper you mentioned that it might be possible to consider a more general setting when you're, so for instance, on the path, when you consider some LTL formulas to be, that must be satisfied. So do you think there might be a general approach to handle that?
Yeah, so what our example orders here can be also expressed as LTL formulas, but I don't think that there is a general approach giving you some nice complexity, because the complexity behavior of the problem was really dependent on the chosen order, so on the precise LTL formula. So I don't see what a general approach can help here.
Do you think it still will be in p-space?
Yeah, it depends on how much you must. Well, if you think of this orders in this order setting, I would say so, because you can simply enhance your power set construction in order to know what you have to what pair of your order is still causing some constraints. But if you're now having really completely arbitrary LTL formulas, I'm not quite sure.
Okay, thank you.
Okay. Other questions? If not, let's thank Petra again. The next talk. So who's giving the next talk?
Me.
Good. So, Petra continues with the next talk: synchronization of deterministic visibly pushed down automata.
Yeah. So thanks again. Now, this work is a joint work together with Henning Fernau. And here we wanted to generalize the concept of synchronizing a finite automaton to pushdown automata. And we already did this for arbitrary general pushdown automaton, which was presented as MFCF this year. And in this work here now, we're again coming down from arbitrary pushdown automaton to visibly pushdown automaton. So what are the models we are considering here? All models will be deterministic real-time pushdown automata, where the real-time condition forbids for epsilon transitions. We will also consider counter variants, so deterministic real-time counter automata, where counter means that our stack alphabet is unary, so we have only one symbol to push on the stack. And then we are considering the different visibly variants, which I will define in more detail in a second. And finally, we considered finite turn variants, where finite turn means that we restrict the number. If we are looking at the stack height profile of our stack, then we restrict the number of times where the profile can change from increasing to decreasing and vice versa. So what are visibly pushdown automaton? For visibly pushdown automata, we can partition the input alphabet into 3 disjoint sets: a set of call letters, a set of internal letters, and a set of return letters, such that for the call letters, if we read a call letter, we are not reading the stack. We are simply pushing something onto one single letter onto the stack. If we read an internal letter, we're not considering the stack at all. So we are basically performing in transitions in the sense of finite automaton. If we read a return letter, then we read and pop the symbol on top of the stack and go to a next state, but we cannot push something on the stack. And except if we read the bottom of stack symbol, then we do not remove the bottom of stack symbol and just read that we can see the bottom of stack symbol. So for visibly pushdown automaton, the stack height is predetermined by the input word, because we now exactly we can see on our input letters whether we increase the stack, keep it constant, or decrease the stack. Then we also have the class of very visibly pushdown automaton. Here, not only the stack height is predetermined by the input word, but also the stack content. So depending on the input symbol, we know which letter we push on the stack. And then we also had this visibly counter automaton, which is then again that our stack alphabet is unary. And notice that a visibly counter automaton is already a very visibly pushdown automaton, since we only have one symbol to put on the stack, so it's predetermined what symbol we will put on the stack. Then the synchronization problem for deterministic finite automaton again asks for whether there exists a synchronizing word that maps all state of the automaton to one single state. And the complexity of this problem in the finite automaton setting is if we simply want to know whether the automaton is synchronizing at all, meaning whether there exists some synchronizing word, then this problem is easy and can be solved in polynomial time. Whereas if we put any constraint on the synchronizing word such that we asked for a synchronizing word up to some length, then the problem becomes NP-complete. And if we relax the condition that the word must map all states of the automaton and simply ask that it maps a subset of states or to one state, or that we have to map into a subset of states, then the problem becomes p-space complete. So now how can we bring this setting to a pushdown automaton? Well, for sure, we want to keep the condition that a synchronizing word needs to map all states of the automaton to one single state. But then we have still the stack hanging around, and we somehow must talk on how the stack is affected by this setting. And there are three possible ways we considered for constraints on the stack. For instance, we could say that a synchronizing word must, for a synchronizing word, all stacks must be empty after reading the synchronizing word. So meaning that we end in one single state and all stacks are empty, which is basically an initial configuration for an pushdown automaton. Or we could say that, okay, synchronizing a PDA means also synchronizing the stacks so that they don't need to be empty, but they should have identical contents. Or we could say that, okay, synchronizing really should just mean synchronizing the states, and we don't care for the stack contents at all. So we considered all of these three stack models, and then the formal problem definition we are considering as we are given pushdown automaton or a subclass thereof, and we want to know whether there exists a synchronizing word for this automaton in one of the stack models. And to illustrate again the problem, so we are searching for a synchronizing word W that maps all of the states to one single state. And now every run induced by W starting on some state is associated with a stack. So we're having all of these runs in parallel, but for each run, we are in a single stack model. And now our empty stack model restricts that after we apply the word W, we end up with an empty model in each run, an empty stack in each run. The same stack model says that we end up with the same content in the stack in each run. And in the arbitrary stack model, the stacks can be simply anything. Now, for a general pushdown automaton, the complexity of this problem in each stack model was that the problem is undecidable, and it's even undecidable for counter automaton. And therefore, we decided to look into a more restricted class of pushdown automaton as the visibly pushdown automata, since they also share in other aspects some nice properties with regular language. The languages of them share some nice properties with regular languages. So we thought that they are a good candidate to look into this synchronization problem. And it turns out that in the empty stack model, all of the visibly pushdown variants behaved as finite automatons. So their synchronization problem is solvable in polynomial time. Whereas if we look into the same stack model and the arbitrary stack model, we have for general visibly pushdown automaton that the problem is at least p-space hard. So in the same stack model, we also have containment in p-space, but in the arbitrary stack model, we only have p-space hardness. And this is also an open problem to find the precise complexity of the variance in the arbitrary stack model, since here we don't have membership. Then if we go into a smaller class like very visibly pushdown automata, where also the stack content was predetermined by the input word, then in all three variants, the problem is solvable in polynomial time. Now, finally, we have these two problems I have not defined yet here in the table. The automaton class is visibly pushdown automaton, and this extension here, no return and return, refers to the set of return letters. And in the no return variant, the set of return letters is empty. So we have no letters with which we can read something from this stack. And in this case, the arbitrary model becomes easy, while the same stack model is still p-space complete. And in the other variant, we are only consider input visibly pushdown automaton, where the set of return letters is non-empty, so that we have the promise that we have some return letter with which we can read the stack, and then the complexity changes and the problem becomes easy in the same stack model and is still hard in the arbitrary stack model. And this is quite interesting because here is the first time that we observe a difference in the complexity of the same stack and arbitrary stack model, because previously in the for general pushdown automata and restricted versions like restricting the number of terms, these two models behave the same. And while restricting the number of terms in the general case lead to a drop in complexity, meaning that the problem became decidable, if we restrict in the number of terms for visibly pushdown automata, we see a rise in the complexity in contrast to the general case. Okay, so thank you again from my side. And do you have any questions?
Thanks a lot, Petra. So other questions?
I have a question again. So in the case of polynomially solvable, so in the empty stack case, essentially, can we formulate any meaningful generalization of the Cherney conjecture? So since we have since we at least can decide in polynomial time that an automaton is synchronizing, can we say anything about the length of synchronizing word, which would be hopefully polynomial?
I think this is promising, but we have not gone in this direction so far.
Thank you.
Thank you.
So could you explain the intuition behind this switch in complexity? For no return, the arbitrary stack model is simpler, whereas DVPDA return, the same stack model is simpler.
Yes, for the no return variant, we have no letter with which we can read something from the stack. And if in the same stack model, we still restrict that the stack contents are identical. So therefore, we can write a protocol on the stack and only accept if these protocols coexist. And on the other hand, in the return variant, when we do have a return letter, then we can then the problem is in the same stack model is equivalent to synchronizing in the empty stack model, because if we can synchronize in the same stack model, we have the return letter which can pop the stack. And on the other hand, if the stack is already synchronized in the empty setting, it's also the same thing. And for the arbitrary stack model, if we have no return letter and we don't care on the content of the stack, then it's just a garbage tape. You have to use it. Whereas if we have a return letter, we must keep the stack, and then we can again write something on the stack which could split synchronized runs again, because the contents matter again.
Thank you. Are there other questions? Okay, let's thank Petra again. Let's thank all the other speakers too. So, Sunil, Bhaskar, are there any announcements? I hand over to you.
No, nothing. Tomorrow we start at the same time, 2 o'clock. I mean, whatever. Indian time, 2 o'clock, but yeah, the same time as.
And today's invited talk is at 8:30 p.m. Indian time.
In 3 hours, right? Just about 3 hours.
There's an invited talk.
Yeah.
In about 3 hours.
Okay, thanks a lot.